In this recording, I'm going to talk about acids and bases. So we'll get started with this chapter. What you're seeing here is a picture of a swimming pool, and one of the common acids that is added to the swimming pool is muriatic acid. It is nothing but concentrated hydrochloric acid. And you do know the formula of concentrated hydrochloric acid. Concentrated just means the concentration, that it's very concentrated. There's a lot of HCl and very little water, but you need to write the AQ to indicate that it is an acid. So it's one of the common applications of acids is to maintain the pH or the acidity of swimming pools, and that is done by adding concentrated HCl. So fairly straightforward chapter. Half the chapter is qualitative, the other half chapter is quantitative. And I do cover the quantitative aspects, but I'll tell you what's really important for the final exam as well. We'll begin with the definition of acids, what's meant by an acid, what are the properties or the characteristics that tell you that you have an acid. Acid is any substance that releases hydrogen ions into water. So you take an acid and you add it to water. Okay. So this is an aqueous solution. You add it to water. What you're going to have is the release of hydrogen ions. This is not exactly how I would continue to write the equation, but this kind of tells you that this would be the definition of an acid. Okay. You can detect acid qualitatively, which means you can use a chemical test, and that test would be to use a litmus paper. Litmus is basically, crushed up plant leaves. It's a pigment found in some plants, which will change color depending on the acidity of the soil. So if the soil is very acidic, that plant actually turns red. So if you take a blue litmus paper and bring it in contact with an acid, it will turn red. So blue litmus is a classic test that's used for acids. Acids have a sour taste. This doesn't mean that you taste acids in the lab, but if you take any kind of produce or any commercial product that is used in cooking, like vinegar, lemons, limes, they all have a sour taste, and the sour taste is a result of an acid that's present in these compounds. So lemons and limes have citric acid, vinegar has acetic acid. So now we're going to take a look at properties of bases, and then I'll back up to look at the two pictures on these slides. A base is a substance that releases, what it's going to release is a hydroxide ion into water. Okay. Just like a litmus paper test is used to identify an acid, red litmus turns blue. So this can commonly lead to some confusion. So you want to make sure that you have this written down and learned well. Blue litmus will turn red in the presence of an acid. Red litmus turns blue in the presence of a base. So red litmus is used as a test for bases. Bases have a slippery, soapy feel. Good old days, soaps contained sodium hydroxide as a base. It's also known as lye. Okay. So that was what gave the soapy feeling, the slippery feeling to soaps. Bases also have a bitter taste, like Pepto-Bismol, milk of magnesia, all of these contain bases. So let's back up, look at this particular picture here. What you're seeing here is it's not just a blue litmus paper, but it's a more specific paper. It's called the pH paper. You can take the pH paper, and when you bring it in contact with the acid, it will give you different colors. Depending on the color, you can match. So the color matches this particular red color, then you're going to say its pH is 2. pH is a measure of acidity, and we will learn about this in detail in the second part of this lecture. Okay, so when the pH is less than 7, it is defined as an acid. When the pH is greater than 7, it's defined as a base. When the pH equals 7, it is said to be neutral. What you're seeing here is a litmus paper. This is the red litmus paper. So if you put it in acid, you can see how it has changed its color into blue. So this does not quantify or measure the acidity, it just tells you whether it's an acid or a base. So litmus paper will just indicate whether it's an acid or a base. whereas pH paper will give you some quantification of the acidity. It'll actually put a number on that acidity and the basicity properties. There is a video here that you can watch, which you'll find it quite interesting. Now, acids and bases react with each other in a very classic reaction. This is not new chemistry for you. You already know this. This is called the acid-base reaction, also known as neutralization. In general terms, acid reacts with base. Both of them are solutions in water to give you salt, which is an ionic compound that is soluble in water. And the side product, of course, you're going to get another product that is water. Salt is defined as an ionic compound that is soluble in water. Right? So this is a classic reaction between acids and bases. We will revisit this concept and look at it in greater detail. This is just kind of a review slide here. This is not new information. You did study different types of chemical reactions, and neutralization reaction is one of the types that you studied. But we're backing up to a concept that I said we're going to study in greater detail, and that is the pH scale. The pH scale quantifies whether, how acidic or basic a solution is. A litmus paper will simply tell you whether it's an acid or a base, but a pH paper can give you a number and tell you whether it's a strong acid, weak base, strong base. The pH scale varies from 0 to 14. Smack in the middle, 7, is referred to as a neutral pH. Anything less than 7 is an acid. Anything greater than 7 to 14 is a base. Now, another thing I want to add here is the more you move towards the 0, the stronger is the acid. So I'm going to kind of write this a little bit differently. I'm going to say strength of the acid increases as you go towards 0. Now, strength of the base increases as you go towards 14. So if I take pH 2 and pH 5 and ask you which one is the stronger acid, it'll be pH 2. If you take pH 10 and pH 13 and I ask you which is a stronger base or which is more basic, that is 13. Okay. So let's take a look at this very interesting slide where you can identify a number of products and compounds that you've encountered, if not in everyday life, at least some point in your life, and it's quite interesting. We'll take a look at 7, and that is pure water. So if you take a tap water, for example, that may not show a pH of 7. Okay, pure water is something that's deionized water, which if you came to the lab and actually work, you will be working a lot with deionized water. This is water that has been purified multiple times, and that will show you a pH of 7. So we are going to go to the acidic side, and so we are going to go less than 7. I'm going to go to a very strongly acidic side, and you will find that hydrochloric acid, and everybody knows what M stands for. This is molarity. Also, you can read it as molar. So 1 molar solution of hydrochloric acid is going to show you a pH of 0, very strong. Your stomach acid actually contains hydrochloric acid. That can be anywhere between pH 1 and 3. Your citrus fruits, citric acid, like lemon juice, vinegar, and wine contains tartaric acid. So anything that contains an acid is going to show you a low pH. Grapes contain tartaric acid. Orange juice contains citric acid. Normal rain contains a little bit of acid, and that's because of the pollution. Because there's a lot of gases that are acidic, and when they dissolve in water, they will form acids. And that's why normal rain can be slightly acidic. Your coffee, caffeine, it's going to be slightly acidic. Milk contains lactic acid. These are not very strong acids, but you can see that it is less than 7, slightly acidic. Your pH balanced shampoo is not 7, it's actually slightly acidic. So smaller the number as you go in this direction, stronger the acid gets. So I'm going to say strength of the acid increases in this direction, where my arrowhead points in this direction. And as I mentioned earlier, as we go down here, we're going to see the strength of the base increases in the downward direction. And some really interesting ones, eggs, seawater. But what I really want to show you is the baking soda and the antacids. That's why when you have acidity problem, when the stomach acid increases, the pH is going to drop. And you can obviously see why you would use milk of magnesia, Pepto-Bismol, on those kind of things to drop the acidity. Soap is actually slight basic. It's quite basic because it uses sodium hydroxide. Household ammonia is your Windex solution. That is quite basic. Liquid bleach is quite basic. Okay, so you should never mix Windex with vinegar. In fact, when you store household products, you want to keep vinegar and Windex away from each other. Drain cleaner such as Drano contains very strong sodium hydroxide, so it is basic. Whereas liquid plumber, if you take a look at it, it actually contains sulfuric acid. That's a drain cleaner that's actually pretty acidic. 1 molar sodium hydroxide is pretty basic, 14. I always like the slide. It shows you a number of general products that we have kind of encounter at some point in our life and shows us how acidic or basic these are. With this scale in mind, let us go ahead and answer this question. We're going to classify these solutions as strongly acidic, weakly acidic, neutral, basic, strongly basic. Okay, so to review this again, our scale goes from 0 to 14. Right at 7, you have neutral. Anything in this direction, we're going to say that the acid strength increases. So this side is all going to be acidic. This side is going to be basic. And as you go towards 14, the base strength increases. So this is an important piece that you have to remember. Using this, let's see, pH 0, I'm going to say is strongly acidic. Lime juice 2.7, I'm going to say is strongly acidic. Still 2.7 is a smaller number. Distilled water is 7, so I'm going to say neutral. And drain cleaner is 13.5. That takes it very close to 14, so I'm going to say strongly basic. So if you got something like 8 or 9, you can say weakly basic. And if you got something like 5 or 6, you can say weakly acidic. So this will kind of give you an idea where you want to place the weakly acidic, somewhere between 2 and 6, weakly basic, somewhere between 8 and 12, 13 and 14 is strongly basic, 0 and 1 are strongly acidic. So I would say important slide, okay? An important question for multiple choice. Let's get further into the definitions of acids and bases. The first person to propose a definition was Arrhenius, and so it's called the Arrhenius definition for acids and bases. According to Arrhenius, any substance that ionizes in water and produces hydrogen ions is an acid. So I feel like there are a couple new words here, ionizes, and also looking at hydrogen ions from a different concept. So let's take a look at this. I'm going to take a very simple acid, HCl. I'm going to add it to water, which is a liquid. What's going to happen is this is an acid according to Arrhenius. So what it's going to do is give up its protons. So what we have is H plus, Cl minus. So the water is going to grab the proton and become H3O plus. Because it's simply H2O, you're going to add it to H plus. Simple mathematical addition, if you like, that gives you H3O plus. Okay, plus what's left over is the Cl minus ion. You're going to write AQ next to both. Okay, now this, of course, is called the chloride ion. This one is a new word for us. This is called hydronium ion. Let's try another example. I'm going to take nitric acid, add it to water. Now this contains H plus and NO3 minus ion. Those are the nitrate ions. H2O is going to grab the H plus. Same kind of addition is going to give us H3O plus. That's our hydronium ion. Plus, you're going to get the nitrate ion. So according to Arrhenius, anything that gives you hydrogen ions, which will combine with water to form the hydronium ion, is called an Arrhenius acid. Similarly, an Arrhenius base, according to Arrhenius, is any substance that releases sodium, that releases hydroxide ions. So here, instead of releasing hydrogen ions, we're looking at hydroxide ions. So as I slipped up a little bit earlier, I'm going to use sodium hydroxide. It is soluble in water. I'm going to add it to water, okay? So I'm not going to write H2O here. I'm just going to break it down because there's a lot of water there. It's going to give Na plus AQ plus hydroxide ion. So this is your hydroxide ion. So this is a base, okay? Let's take another example. This time I'm going to take maybe magnesium hydroxide. I'm going to break it down. That's going to give me Mg2 plus Aq plus, you're going to get two hydroxide ions. So don't make the mistake of writing like this. That is wrong. So it's going to be two hydroxide ions. Okay. So again, you can define this as a base. It's very easy to find out an acid. An acid, the formula will always begin with hydrogen. The base will always have hydroxide as the anion. Now this process where I'm breaking down these different chemicals and writing it down has two names associated with it. It is called dissociation. So the acid and the base are dissociating. It's also called ionization. So the way I'm writing these equations, 1, 2, 3, and 4, what I'm doing is I'm dissociating the acids and bases. I'm ionizing the acids and bases. So hydrochloric acid ionizes to hydrogen ions and chloride ions. Of course, that hydrogen ion will exist as hydronium ions. Sodium hydroxide dissociates into sodium ions and hydroxide ions. So all of that is explained in these two slides. Next, we are going to take this logically to say why some acids are strong and why some are weak. Okay, so that's going to be my next section that I want to explore here. So I'm going to take hydrochloric acid. I'm going to write AQ plus H2O liquid. I'm rewriting this equation really. That's all it is. No new information yet. Let's say I take 100 molecules of HCl, all 100 molecules will break down, all 100 molecules will dissociate. So I will have 100% dissociation or 100% ionization. So when the dissociation is 100%, ionization is 100%, dissociation and ionization mean the same here is 100%, then the acid is said to be strong acid. What I'm going to do next is take another acid. So I'm going to write this as C2H4O2. That's how I think you know it. This is acetic acid. I'm going to write AQ plus water, L, and then I'm going to write C2H3O2. This is your acetate ion. AQ plus H3O plus. You can write H3O plus first and then this, it doesn't matter. But let's say I take 100 molecules of acetic acid, which is your vinegar kind of thing. Maybe 1 to 2 molecules dissociate. So there's 1 to 2% dissociation. Therefore, it is defined as a weak acid. Now, we've come up with a definition for ionization, using ionization and dissociation to define the strength of an acid. An acid is said to be a strong acid if it undergoes complete ionization. An acid is said to be weak acid if it does not undergo complete ionization. So what I'm going to do is kind of change this arrow a little bit. Here I'm going to have a single forward arrow because all 100 molecules will dissociate. Here I'm just going to have a little arrow, and the backward arrow is going to be really big because only 1 to 2 molecules will dissociate. Anything else that dissociates, it's going to recombine to form acetic acid. So this kind of weak arrow, this kind of a double arrow here, the equilibrium arrow, is indicative of a weak acid. Now let's look at some examples here. So we have Examples of strong acids, you don't have to memorize these, but these are your strong acids. Then we have a list of weak acids like vinegar, carbonic acid, hydrofluoric, phosphoric acid, and these are all considered weak acids. So now you know why on your salad you want to sprinkle some vinegar and not hydrochloric acid. So hydrochloric acid will simply destroy your salads. Okay, whereas acetic acid does not undergo complete ionization, so the ions are not going to be present to such a large degree that they would cause tissue damage. So if you get acid on your skin, what's causing the tissue damage are these hydrogen ions and whatever anion is being formed. They enter through the cell membrane, disturb the concentration of the ions in your cells, and cause cell death. So key point here that I've already explained is you have 100% ionization for a strong acid. For a weak acid, you have really less ionization. I really like to write it like this, okay? And we already know what a hydronium ion is. I introduced that right away at the beginning of the lecture. So nothing different with strong bases and weak bases. They're going to flow very similarly like your strong acids and weak acids. So a strong base is 100% dissociation. A weak base is going to be much lesser dissociation, usually very slight, 1 to 2%. So it's very easy to remember an example of a weak base. There's only one here in the list. That's ammonium hydroxide. Okay. So I do not expect you to memorize these. So no need to memorize this and no need to memorize this table either. No need to memorize this, okay? So not much of a difference. You can see 100% dissociation makes sodium hydroxide a strong base. Less dissociation makes ammonium hydroxide a weak base. Okay, so it's kind of difficult to handle sodium hydroxide. It's pretty corrosive. Ammonium hydroxide is your Windex solution. And if you get a little bit on your skin, not great, but you don't have blisters or anything. Now we're going to get into neutralization reactions. I did say we're going to talk about it. So it's going to be a little bit of review, but it's also going to help us learn some new things. So let's start with a very simple example, which is going to be hydrochloric acid. So this is on the PowerPoint, but I'm going to go into some detail here. And then sodium hydroxide, AQ, and then we're going to predict the product. So let's see how. The question is, how do you predict the products of the neutralization reaction? Really important. You have a question or two on the final on predicting the product. The first thing you want to do is break this down. So you want to break it down into, ions. So this is going to be H plus ion, Cl minus ion. Those students who like can write AQ there, okay? I don't usually do it because I don't want to have it all cluttered, so I don't. But you are more than welcome to do that. Now what we're going to do is the opposites will attract positive with a negative, this positive with a negative. So you should kind of have an idea of what we are doing. This is nothing but a double replacement or a double displacement reaction. Neutralization reaction is a special kind of double replacement, double displacement reaction. So Na plus combines with Cl minus, so that's going to give you NaCl. And this is a salt. That means it's an ionic compound soluble in water. So you're going to write AQ. H plus is going to react with OH. So it's going to give HOH. That is nothing but H2O. L. Then you need to balance the equation and you'll see that it is automatically self-balanced. Okay. So let's go ahead and look at a couple problems here. What we're going to do is complete and balance the following neutralization reaction. Let's start with the first one. We have nitric acid. So I'm just rattling off the names here. Hopefully you guys remember. Then we have calcium hydroxide, right? So we're going to break this down into ions. So this will be H plus ion and this will be nitrate ion. So the cation in acids is hydrogen. Everything else becomes, once you remove the cation, everything else becomes anion. Calcium belongs to group 2, so it's 2 plus ion. Common mistake. Don't do this. This is not right. Hydroxide is just OH minus. Okay. So you have two hydroxides. Those students who want to write it can write it like that. It's up to them. I don't. I just write the hydroxide. I don't worry about the two. I'll take care of it in balancing. Now we're going to connect the opposites. So calcium is going to react with nitrate. So you're going to use a crossover method. So that'll be your salt. So salt, we're going to write AQ. H plus combines with OH minus. We're going to write that as water, liquid. This is not a balanced equation, and now we'll balance it. We have two nitrates, so we're going to put 2 in front of that, and that'll give us also 2 waters. That'll give us 4 hydrogens and 8 oxygens on either side. So we have completed this neutralization reaction and then balanced it. That's why I don't use the 2 there, so I can take care of that 2 in the balancing. So what I'm going to do is work out the second problem here. Now H2CO3, you want to kind of think about the formulas. This is carbonic acid. It's going to react with barium hydroxide. Acids and bases will react to give you salt, which is soluble in water, and then you need to get water. You need to get H2O. So what we're going to do is do not do this. This is wrong. Hydrogen ion is not H2 plus, so it's actually H plus. If you want to write 2H plus, you may do that, but I don't. I take care of that 2 in balancing. Then I have carbonate, which is 2 minus. Barium belongs to group 2, 2 plus. Do not do this. This is wrong. Hydroxide is just OH minus. If you want to write this 2 in front of it, you can. As I said, I don't. Now what we're going to do is the opposites are going to react. So barium is going to react with carbonate. You do not use the crossover method. The charges are exactly the same. So you simply combine it. And then H plus is going to react with OH minus. You simply combine it and write water. All right, the reaction is automatically balanced. You do not have to balance it. It will be all balanced on the left and the right side. So very important, you'll be asked to predict the products of the neutralization reaction and maybe asked to balance the equation. But this really, really, really important, knowing how to predict the products. So you'll see a question or two on the final. Moving on, we are looking at Bronsted-Lowry acids and bases. This is a second type of definition used to define acids and bases. If you're wondering why we need a second definition, our Arrhenius definition does not really cover all substances that act as acids and bases. As more and more substances were discovered, it was found that some substances do not give protons when added to water, but still the pH is less than 7. They were still acidic. Some of them did not have hydroxide ions, so they didn't give hydroxide ions when you add it to water, but the pH was greater than 7. So what I'm saying is you can have substances that don't give hydrogen ions and are still acidic, substances that don't give hydroxide ions and water, but still basic. So the chemists felt they needed a broader definition, and that's what is Bronsted-Lowry acids and bases. You can also call it the Bronsted definition. A Bronsted acid is defined as a proton donor. A Bronsted base is a proton acceptor. So proton is H plus. So anything that donates a proton is an acid. Anything that accepts a proton is a base. So I'm going to start off with a simple example, HCl. I'm going to react it with sodium hydroxide. We have already done this equation. We know what the products are, NaCl, AQ, and then H2OL, and it is a balanced equation. Now, if you take a look at this, H plus and Cl minus, this one gives up the proton. So this is a proton donor. We take this is Na plus OH minus. OH minus accepts a proton. So this is a proton acceptor. So HCl donates the proton. Sodium hydroxide, the hydroxide accepts the proton. Therefore, this is the proton donor. So this is the Bronsted acid. This is a proton acceptor. So this is the Bronsted base. You can write Lowry after that. I'm just keeping it simple and saying Bronsted acid, Bronsted base. So we need to find which ones donate protons and which ones accept protons. So let's do a little couple problems here to get the hang of that. So we are going to start with the first one. So let's take a look. I'm just going to write it all without the AQs. Just kind of to keep it clean for me to explain, okay? Nothing else. And then I'm going to write the products as given. I'm just not writing the subscripts A, Q, and L. Now this one I'm going to break it down as H plus C2H3O2 minus. So this one's going to donate this proton. So proton donor. So this is a Bronsted-Lowry acid. This is Li plus and hydroxide. Hydroxide accepts the proton to become water. So this is a proton acceptor. So this is going to be Bronsted-Lowry base. This is also a hydrogen donor, so therefore it is also an Arrhenius acid. This is a hydroxide ion. It can give hydroxide ions when you add it to water. So this is also an Arrhenius base. So in this case, they both are Bronsted acids and Arrhenius acids. This guy is a Bronsted base and an Arrhenius base. Both definitions work in this case. We're going to take a look at something where both definitions don't work like that. So let's take a look at B. I'm going to just copy this down, fully balanced. This is ammonia, or if you like to use the IUPAC name, it's nitrogen trihydride. It's rarely called that. The common name is quite popular. First and foremost, a very striking thing that I see is I don't see plus H2O. I don't see water form, but this is an acid-base reaction. It forms salt, but it doesn't form water. Let's see what this means. So we have NH3, and then we have H2SO4. So what we have here is H plus, and then we have SO4, 2 minus. So right here is your proton donor. So this is your Bronsted acid. It'll also give hydrogen ions in solution. So it is an Arrhenius acid as well. This one has no hydroxide ions, so it is not an Arrhenius base. For something to be an Arrhenius base, you gotta have hydroxide ions. I don't see hydroxide ions. But take a close look at the change in the formula. NH3 becomes NH4. So it has accepted a proton. So it is a proton acceptor. So it is a Bronsted-Lowry base. It's not an Arrhenius base, but it's a Bronsted-Lowry base. So sometimes both definitions will lead to the same answer, Bronsted and Arrhenius. Sometimes one definition will not work. They don't lead to opposite answers. Let me rephrase that. Both definitions can be applied to sulfuric acid. This is sulfuric acid. However, in this case, you cannot call ammonia an Arrhenius base, but you can certainly, it is a Bronsted base. So this is a great example where the Bronsted-Lowry definition can be used for both ammonia and sulfuric acid, whereas Arrhenius can be used only for sulfuric acid, cannot be used for ammonia. Okay. So that's where the qualitative aspect of acids and bases ends. I always teach a little bit of quantitative, which is calculation of pH. I'll go ahead and make a separate lecture on that. But in terms of course competency, your syllabus ends here. What I like to do is teach a little bit more, and because I always have time to teach a little bit more, so I'll teach some calculations, and I won't ask all kinds of calculations on the final. I'll tell you in the lecture which calculation is really important. But that's where your syllabus ends. So I'll stop this recording here and start a new recording. Okay?